Alright students, welcome back. This is a short video that I wanted to shoot on bond enthalpies. So, in the last video we talked about the overall enthalpy or the reaction energy of the reaction. And there is a chemical principle that we can figure out whether a reaction is exothermic or endothermic based on just the energies involved in all of the individual bonds that form the chemical reaction. The way we do that is through a bond enthalpy table. This bond enthalpy table shows the energy involved in forming each of these individual bonds. And again, the energy that would also be the energy required in order to break that bond. So for example, there's a whole table of different single bonds here. A bond between carbon and hydrogen, when it forms, will release 413 kilojoules per mole of that type of bond. A carbon-carbon bond will release 348 kilojoules per mole. And conversely, it requires an input of 348 kilojoules per mole of energy in order to break this carbon-carbon bond. And we can do that for all the bonds that we will deal with on a regular basis. These bond energies were developed over time using some very precise science, usually involving bomb calorimetry, which is a really neat thing that I won't cover here, but you can definitely feel free to ask me about. So from this, we know the energy involved in individual bonds, so we can then take that knowledge and apply it to a reaction in order to give us the delta H of the reaction. The delta H, the change in energy of the reaction, is going to be equal to the bonds broken, which will be positive delta H because that's energy that has to go in order to break those bonds, minus the energy of the bonds formed because forming those bonds releases energy to the outside. So let's again take a quick look at our Haber process to see what we mean here. So in our Haber process, we combine one nitrogen molecule with 3 hydrogens to create 2 ammonia molecules. So what that involves is we have a nitrogen-nitrogen triple bond, which we know from drawing the covalent structure of nitrogen. It looks sort of like this. There are these unpaired electrons on the outside so that everyone has an octet. And we know that a mole of these bonds, breaking a mole of these bonds would require 941 kilojoules of energy because of this number right here. It takes 941 joules to break a nitrogen-nitrogen triple bond. And here we have a hydrogen-hydrogen single bond, so we take a look at that part of our table, and we see that it requires 436 kilojoules of energy to break 1 mole of hydrogen-hydrogen single bonds. We have 3 moles of hydrogen-hydrogen single bonds, so we multiply that 436 by 3, and that covers all the bonds that need to be broken. So we will, in the process of this reaction, break all of the bonds of our reactants, and then we will reform those bonds on the product side. So for our products, the bonds that we're forming is we're forming 2 ammonia molecules, and each ammonia has 3 nitrogen-hydrogen single bonds. So we go to our table and we looked at nitrogen-hydrogen. Each nitrogen-hydrogen bond forming releases 391 kilojoules of energy. So in total, we have 2 moles of ammonia, which means that we have 6 moles of nitrogen-hydrogen bonds forming. So we take that 391, we multiply by 6, because we have 6 nitrogen-hydrogen bonds in 2 ammonias, and that gives us our totals. So then we add up the bonds broken, which gives us a total of 2249, and we subtract the bonds formed, which gives us a total of 2396. That gives us a delta H value for this reaction of negative 147 kilojoules per mole. So every time we undergo this reaction cycle, every time we pass a mole of hydrogen and 3 moles of a mole of nitrogen and 3 moles of hydrogen to create 2 moles of ammonia, that process will release 147 kilojoules per mole of energy. So that's how we calculate delta H. It's all involved in the energies of the specific bonds. We'll be doing some practice on this tomorrow, so I hope that helps. Leave me any questions in the comments. Thank you very much, and I will see you in class.